In 1971, two physicists put very precise atomic clocks on passenger jets and flew them around the world. When the planes landed, they compared the clocks to identical ones that had stayed on the ground. The airborne clocks had measured less time. Not by a lot, a few hundred nanoseconds, but enough to confirm a prediction Einstein had made 66 years earlier from an armchair with nothing but thought experiments. Time actually passed more slowly on the moving plane. Not the clock's mechanisms. Time itself. Einstein's argument starts with one assumption: the speed of light is the same for all observers, regardless of how fast they are moving. This is not obvious. It contradicts everyday intuition. But every experiment ever done confirms it. Now imagine a clock that works by bouncing a light beam between two mirrors. Tick, light goes up. Tock, light comes back. If I carry this clock past you at high speed, from your perspective the light must travel a longer, diagonal path, because the clock is moving sideways while the beam is in flight. But the light still travels at c. A longer path at the same speed means more time between ticks. My clock is running slow, from your point of view. The mathematics gives a precise answer. If I move at velocity v, you observe my time running slow by a factor gamma, which equals 1 divided by the square root of 1 minus v squared over c squared. At everyday speeds, walking, driving, even a jet, v over c is tiny, and gamma is barely larger than 1. At 90% the speed of light, gamma is about 2.3, my year is your 2¼ years. At 99.9% c, gamma is 22, my year is your 22 years. The closer to c, the more dramatic the gap. This creates a puzzle called the twin paradox. Suppose your twin climbs into a rocket, flies to a star 4 light-years away at 90% of c, then returns. From your frame, the round trip takes about 9 years. Your twins' clocks ran slow by a factor of gamma, so only about 4 years passed for them on the ship. You have aged 9 years. Your twin has aged 4. You are 5 years older than your identical twin. This is not science fiction. Particles accelerated in the Large Hadron Collider experience exactly this: their internal clocks tick slowly, which is why unstable particles last long enough to be detected. There is a practical consequence you use every day. The GPS satellites orbiting Earth move at about 14,000 kilometers per hour. Special relativity says their clocks tick slightly slower than ground clocks. General relativity adds a competing effect: the satellites are higher in Earth's gravitational field, which makes their clocks tick faster. The net result is a combined drift of about 38 microseconds per day. That sounds trivial. But GPS calculates your position by timing light pulses to within nanoseconds. A 38 microsecond error accumulates to about 11 kilometers of position error per day. Every GPS system in the world applies Einstein's corrections in real time. Without relativity, your navigation would be unusable. Einstein began with a question a 16-year-old could ask: what would the world look like if you rode alongside a light beam? He sat with that question for 10 years, and the answer unraveled absolute time, the idea that there is one universal clock against which all events are measured. There is no such clock. Each observer carries their own. The faster you move, the slower it runs. The universe does not run time. It hands out a ration of it based on your speed and position, and the ration differs for every one of us.